All right, welcome back to another lecture. In this lecture, we're going to discuss other kinds of probability distributions. We've seen the binomial distribution and the normal distribution already, but what I want to do in this section is just kind of introduce the topic of probability distributions more generally, and then we'll talk about a couple more specific probability distributions that we haven't covered already. So go ahead and give the video a pause and make sure you have the notes ready to go, and we'll dig in. So first of all, let's talk about random variables, right? We've talked about the binomial random variable and we've talked about the normal random variable, but just more broadly speaking, more generally speaking, a random variable is a variable that has a single numerical value determined by chance. Okay, we'll usually use a capital X to represent a random variable, and to see what we mean by this definition, let me give you an example, right? So the outcomes of flipping a coin 2 times are, well, if we flip a coin twice, we could get heads both times, right? So it could be heads and heads. Or it's possible we could get heads first and then tails. Or it's possible we could get tails first and then heads. Or it's possible that we could get tails both times, right? So those are the possible outcomes of flipping a coin twice. We make a random variable out of that by counting up the number of times that something occurs, or by measuring the number of times something occurs, or something like that. In this case, if x is the number of times that heads occurs, then x is a random variable. Note that there are only certain values that x can take on. For example, it's not possible for x to be less than 0. Right? X can't be a negative number because you're counting up the number of times that heads occurs. So it's not you can't say, oh, I flipped heads -7 times, right? That just doesn't make sense. So so the probability x is less than 0 would just be 0. Similarly, it's not possible for x to be more than 2 because again, you're only going to flip the coin twice, so you can't flip heads 3 or 4 times if you're only flipping the coin twice. So the probability of x being greater than 2 would also be 0. But x could be 0, or x could be 1, or x could be 2, right? It's possible that you never flip heads, that you flip the coin twice and it comes up tails both times. In fact, the probability that that happens is going to be 1 out of 4, right? There's one outcome here where heads didn't occur at all, right? The probability x is equal to 1. Well, again, x is the number of times that heads occurred, and there were 2 outcomes where heads occurred once. Okay, so there were 2 outcomes where x equals 1. So the probability x equals 1 would be 2 out of 4. Or we could reduce and get 1/2. And then finally, the probability that x equals 2, well, there was only 1 outcome where heads occurred twice. So the probability x equals 2 would be 1 out of 4. Okay, so in other words, there are 3 possible values that x could take on. It could be 0, it could be 1, or it could be 2. Now, which of those values it takes on is completely determined by chance. And so that makes x a random variable, right? The possible values of x are 0, 1, and 2. So that's the idea of random variables generally. It's kind of a vague notion, but as we've seen in the past, right, if that random variable follows certain rules, if it adheres to certain criteria, then it's a binomial variable, or it's a normal variable, or we'll learn about some other kinds of variables. Okay, let's also introduce briefly the concept of a probability distribution and a probability density function just generally. Again, we've looked at particular kinds of probability distributions, the binomial and the normal. But just generally, a probability distribution is just a pattern, right? It's a pattern of how probabilities are spread across the possible outcomes for a random variable. A probability density function is a rule that's attempting to describe that pattern, okay? So it's a rule that tells us the likelihood that a random variable takes on a particular value. We've already seen a couple of probability density functions, or PDFs, right? Here's the PDF for a binomial random variable. Here's the PDF for a normal random variable. And of course, there are others. Sometimes for convenience, we'll give that probability density function as a table instead of as a formula. For example, if x is the number of times that heads occurs in 2 coin flips, as we just discussed above, then the probability distribution for x would be, well, we said the probability x was 0 was 1/4. Okay, the probability x was 1, we said was 1/2, and the probability x was 2, we said was also 1/4, right? So that would be the probability distribution for that particular example. So in this case, right, we're describing the distribution by just giving a table. One more thing to say about this, like any variable, a random variable can be discrete or it can be continuous. The binomial variable was a discrete variable. The normal variable was a continuous variable, right? So random variables can be discrete or continuous, just like any other variables. And just as a reminder, a discrete variable is one whose values are obtained by counting, and a continuous variable is one whose values are obtained by measuring. Okay, so that's kind of the difference between those things. In the coin flip example, of course, x was discrete because we were counting the number of heads that occurred. But it's important to understand if the variable you're looking at is continuous or discrete, because when we go to compute probabilities in Desmos, for discrete variables, we'll have to make certain adjustments at certain times. And we saw this with the binomial distribution, okay? Whereas with continuous variables, we don't have to make those same kinds of adjustments. So more on that later. Don't worry about it too much, but we'll get there by the end of the section. Let's just look at an example for now, okay? So here it says, in the following table, the random variable x represents the number of marriages an individual aged 15 years or older has been involved in. So we have this table here, right? And it looks like the probability that somebody has never been married is 0.272, right? And the probability that somebody's been married twice is 0.121, and so forth. We're asked in part A, is x, right, is x discrete or continuous? And then a follow-up question, is it binomial, normal, or neither? Okay. Well, first of all, as to the question whether x is discrete or continuous, we're counting up the number of marriages that somebody was involved in. So clearly x is going to be discrete. Okay. Is it binomial, normal, or neither? Well, let's see. A normal variable is a continuous variable, and this variable is discrete. So right off the bat, we can rule out that x is not normal, right? That's not going to be the case. It could be binomial, though, potentially, because it is a discrete variable, and a binomial variable is a type of discrete variable. So maybe it's binomial, but let's see. In order for it to be binomial, there have to be two mutually exclusive outcomes, and you have to be recording the number of successes. In this case, I don't think that's what's happening, because it looks like in this case what's happening is we're just recording the number of marriages that somebody's been involved in. So I would say it's not binomial either. I would say this is neither. It's a discrete variable, but it's neither binomial nor continuous. Nor normal. So it's neither binomial nor normal. Okay. So that just goes to show you that there can be random variables that are neither binomial nor normal, right? There are other kinds of random variables. Part B, what was the probability that an individual was involved in 2 marriages? This is one of those types of problems that seems more challenging than or it seems easier than it should be, but actually it is as easy as it seems, right? This is just a question asking you whether or not you can read the chart, right? The probability an individual was involved in 2 marriages is 0.121, and that's all there is to that, right? Okay. Part C, what was the probability that an individual was involved in at least one marriage? At least one marriage. So we want the probability that X is at least 1, right? Greater than or equal to 1. Well, in order to get that, I think we would just add up all of the outcomes that were more than 1, right? So we would say this is 0.575 plus 0.121 plus 0.032. And we can just go over to Desmos and type that into our calculator. Let me pull up Desmos. And I'm just going to open up the scientific calculator for now. 0.575 plus 0.121 plus 0.032 is 0.728. Okay. Let's talk about the mean and the standard deviation of a random variable, okay? We've discussed that for the binomial variable, the mean is going to be n times p, and the standard deviation is going to be the square root of n times p times q. This is something we talked about back in section 2.5. We've also discussed that for a normal variable, the mean is going to be mu, and the standard deviation is going to be sigma. There's really nothing surprising about that, right? But we talked about that in 2.6 as well. To give a more general description for what the mean and standard deviation of a random variable is going to be, if we have a discrete variable, then the mean is going to be, what we're going to do is we're going to multiply each possible outcome x times its corresponding probability p of x, and then we're going to add up the results. Now, at first glance, that may seem kind of like a new thing, but really it isn't. We discussed the weighted mean way back in section 1.7 in chapter 1. And this formula is just exactly the formula for the weighted mean that we discussed back in that section, right? It's the same exact formula. So it makes sense, right, that this would be the mean of a random variable, right? It's just the weighted mean. We're weighting each possible outcome by its probability, right? So it's just a weighted mean. If you look at the formula for the continuous variable, now some of you are probably scared, and I have good news for you. We're not going to actually use that formula. We're not going to use this one. Okay, we'll practice using this one. Okay, but we're not going to use the formula for the continuous variable because most of you haven't had calculus. Okay, but if you have had calculus, right, you could probably look at that formula and you can see how it corresponds to the formula for the discrete variable, right? Instead of summing, we're integrating, which is really kind of the same thing, except that the width of the rectangles that we're summing up are infinitesimally small, right? So, but otherwise it's the same thing. So, anyway. As for the standard deviations, these formulas are a little bit more opaque. Again, we're not going to use the formula for the standard deviation of a continuous variable in this class because most of you haven't had calculus, but we will practice a little bit with the formula for the standard deviation of a discrete variable. And it's a little harder to see where that formula comes from. I'm not going to belabor the point and go through the derivation of that formula. So you'll just kind of have to take my word for it, but you're welcome to look it up if you'd like. It's not going to be a primary focus. I'll just say that, right? One thing that I do want to remind you of is that the mean can be thought of as the expected value. In fact, notice that when I gave the formulas up here, I'm saying the mean equals the expected value, right? So, and you know, they're both given by the same formula, right? Because they're the same thing. So we can think of the mean as the expected value. And the reason I bring that up is just because when we interpret the mean as an expected value, we're usually going to round to the nearest value that makes sense. And we've talked about this already, but let me just reiterate it and give you a couple examples. Okay, so for example, let's say that our random variable x represents the number of pets a person owns. And then we go to calculate the mean of the random variable x, right, mu sub x. And let's say that mu sub x comes out to 3.7421. So it's totally appropriate to say that the average number of pets per person is 3.7421. There's nothing wrong with saying that. But when you interpret this as an expected value, it becomes a little bit strange to say that, right? Like if somebody came up to you and said, well, let's say you asked a random person how many pets they own, what would you expect them to say, right? You certainly wouldn't expect them to say 3.7421, even though that's the average. Because you can't own 0.7421 pets, right? What you would do is you would round. You would say, well, we expect them to own 4 pets, right? So again, when we interpret the mean as an expected value, we're usually going to round to the nearest value that makes sense. Here's another example. Let's say that x this time is the amount of money in a person's bank account. And let's say that, once again, mu sub x is 3.7421. This poor person, right? Or actually, this is an average, right? So this is the average of a bunch of people. So a bunch of people who are broke, I guess. Anyway, so it's totally appropriate to say that the average amount of money in a person's bank account is $3.7421 or whatever. But if somebody asked you, how much money would you expect there to be in a person's bank account? What we would do is round this to the nearest value that makes sense, which in this case would be to the nearest penny, right? $3.74 is what we would say in that case. So again, we're just going to round. When we're interpreting the mean as an expected value, we're going to round to the nearest value that makes sense. Alrighty. Let's look at another example. This one says, in the discrete distribution below, x represents the number of windows in a one-bedroom apartment. Part A says to compute the mean and standard deviation of the distribution. Okay. Well, if x were a binomial variable, this would be easy. The mean would just be n times b. But I don't think that x is a binomial variable in this case because we don't have a success and failure, and we're not counting up the number of successes. We're just recording the number of windows in an apartment. So this is not a binomial variable. It is a discrete variable, though, because we're counting up the number of windows. So we'll use, in order to compute the mean, we'll use the formula for the mean of a discrete random variable, right? Mu sub x equals the sum. I'm just going to copy down that formula, right, from the previous page, but it's going to be the sum of x times p of x. Okay, so we're going to multiply each of the possible values that x can take on by its corresponding probability, and then we're going to add them up, right? So it's going to be 2 times 0.1, all right, 2 times 0.1, plus 3 times 0.2, okay, plus 4 times 0.7. And of course, then we need to punch that into our calculator. So let's head over to Desmos and do that. Okay, so that comes out to 3.6. Okay, so there's the mean. The standard deviation is a little bit more involved. Let me just write down the formula, and then we'll have to do a little bit of scratch work before we actually calculate it, okay? So the formula for the standard deviation is that it's the square root of the sum of x squared times p of x minus the mean squared. Okay, the mean, right, this part of the formula we already know, okay, it's 3.6. We'll just have to square that value, okay, but this part of the formula we're going to need to figure out. So let's do that scratch work, and then we can come back and plug some stuff in. So the sum of x squared times p of x. What this means is we're going to square all of the possible values that x can take on and then multiply those by their corresponding probabilities. So it's going to be 2 squared times 0.1 plus 3 squared times 0.2 plus 4 squared times 0.7. Okay. And then we can punch this into Desmos real quick. 2 squared is 4, so 4 times 0.1 plus 9 times 0.2 plus 16 times 0.7. That comes out to 13.4. Okay, but that's not my final answer. Okay, that's just this chunk of the formula, right? It's 13.4. So what I need to do now is plug those pieces in. So let's do it. So standard deviation is going to be the square root of this sum, right? X squared times p of x minus the mean squared. Okay. So that's going to be 13.4 minus 3.6 squared. And once again, we can head over to Desmos and see how much that is. So square root 13.4 minus 3.6 squared. Okay, comes out to about 0.663. Okay, so that's how we would compute the mean and the standard deviation of just a generic discrete random variable. Okay, Parts B and C both ask some follow-up questions. Part B says, how many windows would you expect a one-bedroom apartment to have? Well, the average number of windows in a one-bedroom apartment is 3.6, but you can't have 0.6 windows in a apartment, right? So how many windows would you expect the apartment to have? We would just round up and say 4, right? We would expect the apartment to have 4. We would expect 4 windows. Okay. Part C says, how many windows would you expect 10 one-bedroom apartments to have? Okay, so if you took the total number of windows in 10 one-bedroom apartments, how many windows would you expect? And you might think 40, because 10 times 4 is 40. But remember that 4 was not the mean. 3.6 was the mean. So really what we should do is multiply 3.6 times 10, right? We would expect 10 times 3.6, which isn't 40, it's 36, right? So we would expect 36 windows. Okay. So that's how we deal with just a generic kind of random variable. You'll notice that it's not a ton of fun. Okay, going back up here to the mean and standard deviation, it's not a ton of fun to have to calculate these things, because especially the standard deviation, it just takes kind of a lot of work. It was much easier when we knew that a variable was binomial, for example, because then we could just calculate the mean by doing n times p, and it was super fast and super easy. So so that kind of begs the question, well, why was it so much easier when we had a binomial variable? And here's something that I think is kind of interesting. Here's how we can kind of prove that this is true, right? For a binomial variable, if you just take the formula for the mean of a discrete variable, and then you plug in the probability density function for a binomial variable, right? If you plug that in for p of x, right? So that you end up with this expression. Then after a lot of algebra and simplifying, you end up with just n times p. And if you want a proof, here's a proof, right? So you're welcome to kind of watch that YouTube video if you want a proof of that to take you through all the steps. But it's really kind of nice, right? It makes it much easier to calculate the mean because we've done all of this simplification here ahead of time. Similarly, for a normal variable, right? If we take the formula for the mean of a continuous variable and we plug in the probability density function for a normal variable, then after a lot of simplification and some calculus, we end up with just mu. And for those of you who are calculus nerds out there, right, you could follow along with this video that proves that, okay? But here's the key takeaway. If we know the specific kind of variable we're working with, then we get really nice shortcuts for computing probabilities, means, and standard deviations. So it's worthwhile for us to try to classify some of the different kinds of variables that we could encounter so that we have shortcuts for doing computations. And so I'm not going to take you through a ton of the different kinds of random variables and probability distributions that we could come across, but I will give you a couple, okay? So first one I want to talk about is the Poisson. And I'm not going to give you the strict definition of the Poisson variable, but loosely speaking, what I would say is that while a binomial variable counts the number of successes in a fixed number of trials, a Poisson variable counts the number of successes in a fixed interval. And usually it's an interval of time, okay? So again, a binomial is going to count the number of successes in a fixed number of trials. In other words, in a fixed number of repetitions of an experiment. A Poisson variable, on the other hand, is going to count the number of successes within a certain period of time, okay? We're going to use Desmos to compute Poisson probabilities, but just for your information, this is the probability density function for a Poisson distribution. In this formula, the Greek letter lambda represents the average number of successes in an interval of length 1. So if we're dealing with time and we want to know, how many successes we have within a 30-second time interval, then lambda would be the number of successes within a 1-second period of time, okay? So for example, the number of accidents at a given intersection in a week, right? That would be a Poisson random variable. We would be counting up the number of accidents in a particular period of time, right? In this case, in a week, right? So that would be a Poisson random variable. Now, since the Poisson variable counts something, the Poisson distribution is a discrete distribution, and that'll be important when it comes time for us to compute probabilities, because it means that we'll have to make the discrete adjustments whenever we're trying to compute probabilities, the probability that x is strictly greater than a number or strictly less than a number, okay? We'll talk about this a little bit more further down, okay? So we'll use the Poisson distribution in Desmos to compute probabilities. As far as the mean is concerned, the mean of a Poisson distribution is lambda times t, where t is the length of time that we're interested in looking at. And the standard deviation of a Poisson random variable is the square root of lambda times t. So that's that's kind of an interesting feature of the Poisson distribution, that the standard deviation is just the square root of the mean. Anyway, let's look at an example. So example 3 here says cars arrive at a particular McDonald's drive-thru at the rate of 0.16 cars per minute between the hours of 3 and 4 p.m. Let x be the number of cars that arrive in any given 20-minute interval of time between 3 and 4 p.m. Part A asks us to compute mu sub x. And then it has a follow-up question. How many cars would you expect to arrive between 3 and 3:20? Okay, well, mu sub x is going to be lambda times t. where lambda is the number of cars. In this case, it's going to be the number of cars that arrive in a 1 minute interval of time. We were given that information here. We were told 0.16 cars per minute, so that's lambda. T is the period of time that we're interested in. In this case, we're interested in 20-minute intervals. Okay, so that's going to be T. So mu, right, the mean is lambda times T. That's going to be 0.16 times 20. Okay. Let me just punch that into my calculator real quick. 0.16 times 20 is 3.2. So between 3 and 3:20 p.m., we expect 3.2 cars on average. Okay, that's the average number of cars that will show up between 3 and 3:20. Now, the follow-up question is, how many cars would you expect to arrive? Well, on average, 3.2 cars will arrive between 3 and 3:20. So on any given day, the number that I actually expect to show up is going to be 3, right? We expect 3 cars to show up. So we expect 3 cars between 3 p.m. and 3:20 p.m. Okay, part B asks us to compute sigma sub x, right, the standard deviation. Well, since this is a Poisson distribution, right, sigma sub x is just going to be the square root of lambda times t. So that's going to be the square root of 0.16 times 20. And let me punch that into my calculator. Square root 0.16 times 20. Well, that's 1.788854382, so approximately 1.8. Okay. And then finally, part C, it says compute the probability that x equals 5, right? We expect 3 cars to show up, but it's possible that 5 cars will show up, or 4 cars, or 12 cars, right? These things are possible. Maybe they're not super likely, but they're at least possible. So what is the probability that x equals 5? Well, to answer that question, we're going to use the Poisson distribution in Desmos. So we'll go to Desmos, but what we're going to type in is Poisson dist. And then we'll open up a set of parentheses, and what we have to put in the parentheses is the mean, right? We have to put in the mean, which in this case was 3.2. Okay, and that's all we have to put in there is just the mean. Okay, and then we're going to try to compute the probability that x equals 5. Now, if x were a continuous variable, we would say, well, that probability is just 0. But x is not continuous, it's discrete, okay? In particular, it's Poisson. And so this should give us a non-zero answer. But in order to find it, the way that we'll have to enter it into the Desmos calculator is as follows, right? We'll have to look for the probability x is between 5 and 5. Okay, so that's how we'll actually enter it in. Let's head over to Desmos and take a look. So I'm going to open up a new Desmos calculator because I want to open up the graphing calculator. And I'm going to type in Poisson dist. And just like with the binomial and the normal, this will turn into normal script as soon as you finish typing it in, unless you've made some kind of typing mistake. And then I'm going to open a set of parentheses, and it tells me you need to enter the mean, right? The mean was 3.2. I can zoom in on this probability. So this is kind of what the Poisson distribution looks like. The shape will change depending on the mean a little bit, okay? And I want to compute a probability, so I'm going to click on the cumulative probability thing. This is exactly the region that I want and I'm looking for the probability that x is between 5 and 5. So then here it will just highlight the one bar that I'm looking for, right? X equals 5. And it looks like that probability is 0.1140, about 0.1140. Okay. Okay, so that's the Poisson. On the homework, or on a problem set, or on a test, I would tell you when x is Poisson, right? That's not something that I expect you to know just by looking at the problem. So I'll let you know when you've got a Poisson variable in your hands. And then when you do, this is the way that you handle the mean, the standard deviation, and probabilities, right? Let's look at another kind of variable, right? So the uniform distribution. The uniform distribution has an interesting connection to the Poisson distribution that we just talked about, and we'll talk about it in a second. For now, this is how we define the uniform distribution. Okay, so a random variable x is uniform if it has this as its probability density function. Again, we're not going to be using this formula by hand, so you don't need to really worry about it too much, okay? But here's what I would like you to understand. The uniform distribution measures when or where something occurs, so it's a continuous distribution, right? So unlike the Poisson, the uniform distribution is continuous. This is the mean of the distribution, and this is the standard deviation. A and B in these formulas represent the endpoints of the interval that we're looking at, okay? So as usual, this kind of thing becomes more clear when we look at an example, so let me give you one, okay? So number 3 here says, cars arrive at a particular McDonald's drive-thru at the average rate of 0.16 cars per minute between the hours of 3 and 4 p.m. Okay, well, so far this sounds exactly like the previous example, right? Another way to say that is that on average a car arrives at the drive-thru about once every 6 minutes. Okay, so a car arrives at the drive-thru at a time x that is uniformly distributed between 3 and 3:06 p.m. So this time x is uniform, right? X is a uniform variable. Part A says to compute mu sub x. And then it has the follow-up question, what time would you expect the car to arrive? Okay, well, for a uniform distribution, the mean mu is A plus B over 2. Okay. A and B are the starting and ending points of the interval that we're interested in. In this case, we're interested in the interval of time between 3 o'clock and 3:06. So we could say that A is 3 o'clock and B is 3:06. You could use military time and say that we're looking for the that A is 1500 and B is 15:06 or whatever, right? Or what you could just do is say that you could just start your timer at 3 o'clock and say the timer starts at 0, okay? So then at 3:06, the timer would be at 6. And that's what I'm going to do just to make the calculations easier. So I'm going to say B equals 6, okay, and A equals 0. So then the mean would be 0 plus 6 divided by 2, which is, of course, just 6 divided by 2, which is 3. Okay, so if the mean is 3, what does that mean? What time do we expect the car to arrive? Well, we wouldn't expect it to arrive at 3 o'clock. What this means is that we expect it to arrive 3 minutes after 3 o'clock. In other words, we would expect it to arrive at 3:03 p.m. Okay, we expect the car at 3:03 p.m. Okay. I think that should make intuitive sense, right? If you've got a uniform variable, then that means that the car is equally likely to arrive at any point between 3 and 3:06. So what time do you expect it to arrive? Right smack dab in the middle, right at 3:03. That's when we expect it. Part B asks for the standard deviation. So the standard deviation for a uniform variable is the square root of b minus a squared over 12. Okay, and I'm just getting these formulas, by the way. I'm just getting them from here when we talked about them on the previous page. Okay. So let's plug in some numbers there, right? We already know that b is 6 and that a is 0. So this is going to be 6 minus 0 squared divided by 12. And now you can just punch that into your calculator and see what you get. Let's take a look together at that. So we'll do square root of b minus a, right? 6 minus 0 squared divided by 12. So it looks like that's about 1.7 or so. Okay, and then finally part C, it says find the probability that the car arrives between 3:01 and 3:03. Okay. Well, we're going to use Desmos, of course. We're going to use the uniform distribution in Desmos. So we'll go to Desmos and then we'll type in uniform dist. And then when you use the uniform dist in Desmos, what it expects you to put in is the starting point and the ending point, right? A and B. So we started at time 0 and ended at time 6, right? 6 minutes later. And now we're being asked to find the probability that a car arrives between 3:01 and 3:03. Well, if 3 o'clock corresponds to time 0, then 3:01 corresponds to time 1. So we want the probability x is between 1 and 3, okay? So we want the probability x is between 1 and 3. Let's head over to Desmos and take a look. So I'm gonna, again, I'm gonna look at the graphing calculator. I can get rid of this one now. And type in uniform dist. Okay, and then I'll put in my starting point, my ending point. I can zoom in on that. Okay, so it's kind of this weird looking function. It's just flat, right? It's just uniform between 0 and 6, and then less than 0 and greater than 6. There's no likelihood out here, but okay, I want the probability that x is between 1 and 3. So it shades in that region between 1 and 3, okay, and computes the probability here, right? The probability is exactly 1/3, right? 0.333. Okay, so this is approximately 0.3333. Okay, so quick aside here, I said earlier that the uniform distribution was tied to the Poisson distribution in an interesting way, and so I just want to comment on that, that if you're thinking that the last two examples were pretty similar, then you're absolutely right. They were very similar. Loosely speaking, here's how the Poisson and the uniform are connected, okay? Loosely speaking, if you're interested in the occurrences of an event in an interval of time, then the number of occurrences is a Poisson variable, and the timing of those occurrences is a uniform variable. So in our example, when we counted the cars that arrived at a drive-through, we used the Poisson distribution. But when we measured the time that a car arrived at the drive-through, we used the uniform distribution. Okay, there are some details there that you would have to kind of hammer out in order to really nail this down rigorously, but loosely speaking, right? That's how those variables are connected. I want to talk about one last specific kind of variable, and that's student's t distribution. This one's a very weird one. First of all, it has a very nasty probability density function, and fortunately for us, we're not going to use it. But it's just so much. I mean, the probability density functions we've seen so far have not been the nicest things in the world, but compared to this, they were a walk in the park, right? So we're very happy that we don't have to actually use this to do these calculations by hand. The reason that I want to show you this distribution, though, is because in the next section, in section 2.8, we'll be using student's t distribution in order to calculate the probability that a sample mean falls within a certain range. So this distribution will become very important for us very, very quickly. Okay. For now, we're just going to practice computing a student's t distribution problem in Desmos, and we'll see the context for it in the next section, in section 2.8. When we go to compute probability involving student's t distribution, we'll have to enter in the degrees of freedom. Degrees of freedom, it's not something that I want to get into in a ton of detail right now, but for student's t distribution, the degrees of freedom is always going to be one less than the sample size. Okay, so whatever the sample size is, the degrees of freedom is one less than that. Let me just give you a quick example. So suppose that t follows student's t distribution with 12 degrees of freedom. Well, if it had 12 degrees of freedom, right, then that means obviously df, degrees of freedom, equals 12. But from that fact, you can deduce that n must have been 13, right? Because degrees of freedom always has to be one less than the sample size. Anyway, and then it says compute the probability t is greater than 2. Well, we're just going to use the t distribution. So in Desmos, we're going to type in t dist. Now, with the t distribution, the first thing that you have to enter is the degrees of freedom, which we're told was 12. Optionally, you can also enter in the mean and the standard deviation of the distribution, and we'll see this in a little bit more detail in the next section. But for now, we're just going to leave it on its default setting, mean 0, standard deviation 1. And so we can just close up those parentheses, t dist 12, right? So you put in the degrees of freedom, and then we're going to calculate the probability that t is greater than 2. Okay. Now, student's t distribution is a continuous distribution. So it works kind of like the normal distribution, in the sense that the probability that t is greater than 2 is exactly the same thing as the probability that t is greater than or equal to 2. And the reason I'm writing it that way is just because that's how it's going to show up in the Desmos calculator. Okay, so let's go over to Desmos and take a look. So I'm going to get rid of this uniform distribution, and let's type t dist and then enter the degrees of freedom. And I'm going to zoom in on that. Okay, and you can see that it looks kind of bell-shaped. In fact, the t distribution is related to the normal distribution. The more degrees of freedom you have, the closer the t distribution becomes to the normal distribution. So it's sort of like an approximation for the normal distribution. I want to compute the probability. I want the region to go to the right so that I can put in the probability t is greater than 2. And you'll notice that it does say greater than or equal to, not strictly greater than, okay? But in the case of a continuous variable, they're exactly the same. So we'll just put a 2 in there, and that's all there is to it, right? So 0.0343. Okay, so that's all I want to do with students' t distribution for now. Like I said, we'll come back to it again soon in the next section. just so that you're aware, there are other kinds of distributions. There's the chi-square distribution, there's the F distribution, and all kinds of other distributions. Just to give you an idea, here's, let me just open this up in a new tab so we can look at it together. But like, here's a chart that has a whole bunch of different probability distributions in it, just so you get an idea of like how much there is here. I'm familiar with some of these, but not all of them, right? And I certainly don't expect you to be the master of all of these different kinds of probability distributions. But that just gives you some sense for like how little of the surface we've really scratched here. There are all kinds of probability distributions that we could talk about. But we've kind of given just some of the main ones that tend to come up more often than not. Let me give you a brief summary, and then we will be good for this section, right? So when we're dealing with probability distributions, there are typically three things that we want to be able to do. Number one, we want to be able to compute probabilities. Okay, if you're given a chart like you were given back in example 1 in this section, then you can just use the chart to read off the probabilities. If you're given a probability density function, then you could try to use that probability density function to compute probabilities. We really didn't practice that a lot, and you're not going to be tested on it. If you know exactly what kind of probability distribution you're dealing with, then of course you could compute probabilities in Desmos, and we'll talk about that a little bit further down. But that's the first thing we want to do with probability distributions, right? We want to be able to compute probabilities. The second thing we want to be able to do is compute the mean, and then the third thing we want to be able to do is compute the standard deviation. And these are the formulas for those things, okay, in general. They're nasty formulas. We don't really like to use them if we can avoid it. And so if we can be more specific about the kind of variable we have on our hands, then we can use shortcuts. And here are the shortcuts that we've talked about, right? So here are the special kinds of distributions that we covered in this section, or that we've covered in the past, right? So for discrete distributions, we talked in 2.5 about the binomial, okay? And then in this section, 2.7, we talked about the Poisson. Those are both examples of discrete distributions, and we have we can compute probabilities in Desmos using those distributions. We can also compute. We also have shortcut formulas for their means and standard deviations, right? For continuous distributions, we talked about the normal distribution in 2.6, and then we talked about the uniform and student's t distribution in 2.7. 2.7, not 2.6. And once again, we can compute probabilities for those things in Desmos, okay, using the appropriate tool. And we can also we also have shortcut formulas for the means and standard deviations for each of those things. We didn't really talk about the mean and standard deviation for students' t distribution. You'll see why in the next section. So we'll just leave that there. Now, the one thing that I want to say is that it's very important to keep track of whether the variable you're dealing with is discrete or continuous, because if you're dealing with a discrete variable, then when it comes time to compute the probability that x is strictly bigger than a, or that x is strictly less than a, we'll have to do a little adjustment, right? Whereas if your variable is continuous, then no adjustment is necessary, okay? So for a discrete distribution, the probability that x is greater than a will be entered into Desmos as the probability x is greater than or equal to a plus 1. And the probability x is less than a will be entered into Desmos as the probability x is less than or equal to a minus 1. Whereas for a continuous distribution, like the normal distribution or the uniform distribution or student's t distribution, no adjustments are necessary. Okay, the probability x is greater than a will just be entered into Desmos as the probability x is greater than or equal to a. And the probability x is less than a will be entered as the probability x is less than or equal to a. So we use these adjustments for the binomial and Poisson variables, and we use no adjustments for the normal, uniform, and t variables. Okay, and that brings us to the end of this section. This was another long one, a little bit on the long side, so thank you for hanging in there, and I will check in with you in the next one.